So this is a presentation of actually a work that has been started in TIPES project that was basically the father of the two projects on tipping points that are ongoing now. And all the work that's done by our PhD student, Matteo Cini. And basically, it's kind of about the collapse of the AMOC and what everybody has talked about the AMOC so far, so I don't need any kind of introduction, but the idea is that what we wanted just to see if we could detect an hysteresis cycle in this model driven by an increasing of CO2. And so basically it's exploring the role of CO2. And we work with AMOC model, which is the plasma LSG, and with T2172 by 76. And we did 3 independent hysteresis simulations, consisting in a very slow, we will see later, ramp up plus a ramp down. In the CO2 concentration. So basically, the increasing of CO2 concentration is really very small, it's 0.2 ppm per year. We already knew that in this model we have two states of the AMOC. One is on and the other one is off. And actually, in the previous paper that was published in 2024 on MPJ, we showed that applying rare event algorithms, we were able, only using internal variability, just to jump to the off states in this model. So let's see the experiments. So basically what we started, from a starting point, the initial conditions were taken from a long control simulation of this model, 2,000 years long at 354 ppm of CO2. And then for 3,000 years, we ramp up, applying this 0.2 concentration per year, and then reaching 9054 ppm. And then we did the ramp down, going back to the original 354. So basically, you have 6,000 years of model simulation and 3 ensemble members. So I'm going to show what we found with the first ensemble member. So we can see here this hysteresis cycle, and the dark blue line is corresponding to the ramp up, and the light blue line to the ramp down. So basically, we got a transition from the on to the off branch of the AMOC at about 70-50 ppm. And then going back at 600 ppm. What it is interesting in this integration is that we can see that at the beginning there is this, sorry, well, what's this one? Is it? Yeah. So basically you can see that there is this oscillation, that are the oscillation basically that are mentioned before, because this model has a very long 200, I think that period is around 200 years of oscillation. And then we can have here kind of jumping back and forth, and this you have a first attempt of a transition. And then we have the transition with this peak. But let's see what happens in the second ensemble member. So the second ensemble member was basically equivalent to the first one, and so the same initial condition in the ocean, but applying a very small perturbation in the atmosphere and in the PCM level. And you can see that actually, well, we can go back and forth, that in this case, the transition happens earlier, and basically you can have these jumps and going back. And also, basically, so around 600 ppm, the transition to the off branch, and about 500 bouncing back. So the third integration is actually different, because in this case, in the case of third integration, we started from a different initial condition from the ocean. So basically 8 years before, and you can see now. So this is even more interesting in a way, because basically we have an inverse hysteresis cycle. So in this case, we have jumping at about 650 and bouncing back at 780s. So basically, what we found that there is kind of interval in which we can expect to have some transitions from one branch to the others of the model. And this transition is basically highlights the importance of the initial condition, so the internal variability in this case. And another thing that I wanted just to kind of highlight is basically the fact that before the transitions, in two of these two, we have also an increasing in the value of the AMOC, which is higher than the natural variability of the AMOC, which in these plots is expressed by this. Sorry, it's very difficult to say, between these two lines. So now to explore what better these things, what we did, we basically, from the first integrations, the blue line, we did the following. Basically, prior the AMOC collapse, we just focused on, we branch 5 ensemble members, keeping the concentration of CO2 constant, and we looked at the behavior of these 5 ensemble members. And you can see that in all integration, but the last one at 714 ppm, there were a difference between these ensemble members. In the last one, all they decline. In the first one is going to decline, the red one, and the others continues their way. And in these two, they are quite interesting, because we can see that some of them, we have this oscillatory behavior, which is quite interesting. It seems that the system is kind of oscillates of might be an unstable limit cycle. And actually, if we take this kind of integrations and we prolong these ensemble members further, one can see actually that this is year 3000. So basically, one can see that this interesting behavior is going to continue. So it might be something that has been also found in the same model by Reichböhmer, who is in the audience now, and I think it's reported in his PhD thesis. I don't know if it is already a paper about that. But this is quite an interesting behavior. Another thing that we wanted just to look at is about the rate-induced tipping. So, also in this case, the role of internal variability. These are different integration, all starting for this initial condition, but what we did is our very short integration, 120 years long, and basically we changed the rate of CO2 from 2 ppm per year to 12 ppm per year. And one can see that none of this system is going to collapse in 120 years. So basically, it seems very important, the period of stabilization. And even at about 5,000 ppm, we don't have the collapse. We didn't find the collapse of the AMOC. However, let's take the first one, 600 ppm. We know that this is very close to the thresholds that we saw below about the collapse. And what we did, actually, we stabilized the concentration of all the 50 ensemble members, and we prolonged the integration for other, how many? I don't remember, 400 years. So basically, you can see here what we saw before, the first 120 years, and here that we have at the same, at 604 ppm, what happened. And it's really interesting because we can see here actually that half of the ensemble members, they stay in their own states, and more or less half they go, and there are some of them, they are going to oscillate. And it's very clear here, we chose some of the ensemble members just to see better the behavior. So basically, this is also another proof of the importance of the stabilization period in terms of looking at the collapse of the AMOC. And the last thing that I'm going to present is that we try to apply early warning signals to see if they could actually say something about what we saw in terms of the shift of the collapse of the AMOC. And here is the restoring rate lambda, and here you can see the variance. In gray, there are these, the AMOC index, and here is the control, and while the background is white are the hysteresis simulations. And the panel D, in both cases, in the panel D, we change the window that we use to compute the restoring rate and the variance. And what one can see is actually the indicator works. Both of them, they work, but not in advance. And we could find a number of false alarms. For example, look at these simulations. And in gray, you see that the indicator actually was very sensitive to the cycle of the natural cycle of the AMOC. And when we got the tipping, basically the indicator went above 0, which is the indication of the tipping, but almost at the same time when we saw the tipping. And for the lambda, for the variance, sorry, it's more or less the same thing. So the idea here is that the indicators are correct, but they can have, in a case in which we have cycle and our continuous variance, we can have many false alarms. So, well, basically, I'm finishing. So basically, these are the conclusion of the talks. That what we found that the presence of a climate internal variability can alter substantially the timing of the tipping event, at least in this model, and in both the collapse and the recovery. And also in our faster increases experiment, we saw that a long stabilization period is necessary. And also that we highlight the fact that five-member simulation that differ only for perturbation can evolve in very different AMOC states, and these results are consistent with what was shown in the paper by Romanou et al. In 2023. And more on some ideas about the use, for example, of the early warning indicators. What we found that actually, in terms of variance, is that the variance indicator is not really reliable when we look at the one integrations, but when we compare the increasing of variance, when we are ensemble members, so the variance, the spread between the ensemble members, this is very good indicators. So it seems that we are in doing ensemble integration. This can be something that can be applied, and I've finished. Thank you, and please tell me.
You can keep it